Hello, everyone. Today, our group of scientists, internationally, they are occupied elsewhere. So I'm just going to stream you the presentation for history of physics today, and then we'll be continuing to discuss that at a later time. Uh, but I'll briefly present the episodes. As we know, we're doing the episodes earlier. Uh, episode 1 to 4, we started with classical physics, what led to the classical physics, and so forth. And then we moved on what the problem was, especially ultraviolet catastrophe, in a sense, uh, that it predicted, you know, unrealistic infinite temperatures, just the local heating elements, things like that, which is totally wrong. So that led to the understanding of Planck's, formulation of energy quanta. But then that developed, and with the Schrodinger equation and all that, the quantum physics really developed, along with general relativity. And then we went through these the other episodes where we saw you know, their contemporary physics. But then both of them eventually went into another set of problems, which is we call it vacuum catastrophe, where predicted unrealistic to high magnitude level, hundreds of magnitude, orders of magnitude difference between observed vacuum energy and quantum field theory predictions. So essentially, we have the vacuum zero point that I and Marcellus have started point physics and then using Helmholtz decomposition, so that we have both the 0 point, which eventually becomes the CMBR, and then in my recent paper, and then later on uh, the micro black hole. These two are quite possible from superluminal noisy general condensate, and that's the new papers I'm publishing shows that. Now, going back to the understanding of history of physics itself is the main focus here. So we don't go into too much detailed mathematics, just enough to explain what was going on step by step and what we know in normal physics, so to say, until now. So that led to the understanding that we are to uh, do experiments to confirm that, or observations to confirm the models, and that has become more and more difficult because it's more and more mathematical. And the string theory is ultimate mathematics kind of, which does not have any observable, so to say. So far, we have not been able to confirm. But many other quantum physics have been, proven. Some of and also the general relativity. It explains some of the things, but the main thing in the new paper, the recent paper that's going to come, is in the scalarizing aspect. Classical physics has very high level of scalarizing in the sense that we can, measure most of the things, like simple things like speed. We can actually measure. So they're all scalar, are measurable, very simple. We use them in everyday life, including temperature, speed. We measure the distances. We have rulers, and then time. Again, I'm talking about tense of time, but the scalar time we measure every day, and the time goes. The event goes on. The time goes on asymmetrically to the future. So all these are measurable. So classical physics, most of it is measurable. Of course, the question of gravity is still up in the air, so to say. So the gravity, you know, how it connects with all that is still a puzzle. And it originally was supposed to say that it is a force, according to Newtonian physics, or Galilean, uh, an acceleration that causes for the masses to create forces. But really, that is the question now. Most likely, most likely, they may not be forces, but just gradients. That's what I am coming to. So these questions remain in conduct gravity. So that's one of the advancing fields. Also, some people are contesting. But in the conduct gravity, if we say that we take care of the force and they say, okay, gravity is just a gradient, not a force. I think, that then conforms to general relativity also of curving, the matter curving space-time, and the space-time deciding how the matter should follow with the equation of motion, so to say, that I mentioned about John Wheeler's spec. So the Einstein, Schrodinger, and I talked about uh, the short side metrics. Things are all they coming to picture. So now we are going to continue with our episode 4 uh, of presentation, and the episode 4 we are going to talk about the how the history of physics unveils. So we are going to talk about the present the aspect of physics uh, where the quantum and the relativity people are trying to see how we can we can really you know, see how the how we can go ahead and then okay. So now we are just adjusting, ensure that we have the slides uh, to present completely, and then trying to get the full screen. So that's the process we are trying to do. All right. So now we have the correct form that we want to present, and then uh, okay. So now I think we are all set to do the history of physics. So I just briefly will go through today, and then we will have more detailed explanations and then discussions, especially Q&A discussions as we go along. But this gives us some time to continue. And as I said, the history of physics episodes are meant to eventually create a documentary movie, things like that, probably next year sometime, for about 6 months, sometime in the summer of 2025, hopefully, we'll start doing that so that, everybody will be able to get an understanding of what physics is because it has become so mathematical, so complex that even the most experts have difficulty in understanding what that is, especially with tensor calculus and things like that. So here we are going to use only applied quantum astrophysics going along. But towards that, we have to really understand how historically they came up, because that's very important. And we can always fall back and then to classical physics. So each time when it is characterized, it has to show that it conforms with the classical physics, because that's the basis on which everything was built upon. Later on, operator, algebra, geometry, things like that. So in this episode, we're going to talk about experimental aspects that proves the theories of quantum mechanics and relativity. So the first aspect is the experimental investigations that verified quantum mechanics to some degree. So the first one is Thomas Young's double slit experiment, and you have this reference. I may not put all the reference, and some I have put a, uh list of references. So please bear with me because the amount of literature is too huge. But we will select some of the key references, and then the rest of it, uh, you can see it. And also, this presentation is not meant to, uh, supersede any of the other, courses or anything like that. We need the courses in physics, quantum physics, general relativity, as well as YouTube videos and experts and professors talking about it to go natural derivations, things like that. So this is just a snapshot of what's going on, what was going on in history. So the double slit experiment showed about the interference pattern. The interference pattern is essentially a bands of light and dark, like a barcode, which challenged the classical views that laid the foundation and then laid the foundation of quantum mechanics. So from classical physics, a continuum, but this shows that that's not the case. So essentially, you can go into detail about that, but I am going to go into too much detail about the slit experiment because there are a lot of many different things that even John has talked about. His in experiment how that he's going on, and then all of the people, Christopher, Emmanuel, myself, Emery Taylor, and Manuel, we are all working on that, and then as we go on, as well as Christian and Gerd, uh, we are looking more into a double slit experiment and, you know, is it really proving the quantum mechanics? That's still a question, but the question of entangled states with the path polarization, hyperentangled photon. So photon pairs have been found to be entangled, and uh, many of the Chinese experiments, other aspects, is proving that actually the photons that are uh, separated or isolated, even very large in space time, can be entangled. So it uses chessboard states having two three-dimensional systems that verify their weak entanglement. So there are many techniques that's used, and I'm not going to go into detail about that. Uh, but this data is derived from moments of randomized measurements. Like I said, experimental verification of bound and multi-particle entanglement, the randomized measurement toolbox. So these are very high level sophisticated experiments. It shows that the photons can be entangled for large distances. Then we have the question of the quantum physics. One of the main thing is quantum physics is the spin aspect. Uh, so when you talk about the spin, the birth of the spin is based on uh, you know based on the the understanding of Gerlach and Stern, who proved that there is atomistic magnetism. So the magnetism occurs at the smallest level, and these between the electric and magnetic fields, you have the interaction with the original Maxwell equation. So they're interactive, they're orthogonal to each other, these fields, and then so they rotate. They cause mutual rotations at the atomistic and also the particle level, which we call it spin. And this has been proved by the Gerlach Stern experiment that's shown briefly here. You can refer to that reference to get more understanding of how that is done. But these experiments are proven uh, about the essentially how the spin is a real thing. So, so is a very important component and of the You have spin for fermion and full spin for bosons and so on and so forth. So the scanning time microscope also, which I used extensively, one of the research called Small Business Innovation Research of on the on the U.S. Navy and the U.S. Air Force and combined together. Uh, so the scanning tunneling microscope, which is now called scanning probe microscope, it, is, it includes atomic force microscope, things like that. But I studied scanning tunneling to actually find the density of states of the electron configuration on the surfaces, and also to process it for diamond and things like that to create room temperature diamond. So we are seeing the feasibility for that. But also I study the aluminum. So the scanning tunneling microscope is a very good, we established, the Nobel laureate Sir Rohrer, whose lecture also I attended. That was the initial stage that we were doing that, and you can see the reference of Rohrer from birth to adolescence, the scanning. So the modern physics review. All right. So now, the next level of microscope, it's a microscope of the quantum microscope, you can say, is the LHC, Large Hadron Collider measurements. So there are many collaborations, uh, including you have yeah, okay. So uh, proton port. Essentially, it is a hadron collection, so it's called hadron. Hadron, like protons are called hadrons. They're composed of the quarks and things like that. So the proton-proton collision is what is creating all the zoo of particles, so to say. So continuing on that, there are many different experiments which have, you know, kind of explained and also to somewhat prove. And there are some questions that remain about these experiments. Uh, but Michelson, Morley, and Kennedy, their experiments proved that the speed of light remains constant regardless of Earth motion through space. So this constancy of the speed of light is what the relativistic aspects is. It essentially uh, confirm or it support the idea of relativity. So it's interactive. Einstein used that and then said that regardless of the observable speed of light is constant. So we use light to to develop the relativity, especially the special relativity with the Lorentz transform and things like that. But then Eisenstein-Stilwell experiment, so you can see the reference there about the study of the atomic clock, uh, showed that a redshift of light emitted by fast-moving hydrogen atoms. So the redshift is very important because eventually, of course, we know Hubble space. Uh, the redshift was the key thing to show that the expanding universe occurs. And that, again, Hubble tension, things like that, is the experiment that's going on to understand because that constant, many other constants are not really constants. So that's one of the very disturbing aspects of the physics that we cannot really unequally say anything is really constant over a very long period of time. So that's a study by itself. But fast-moving hydrogen atoms that we can track, they showed evidence of time dilation. So that kind of, was consistent with the special relativity, and it's kind of, uh, indirectly give a certain evidence or first level proof of the special relativity to some degree. So it's the way we see things. So then Pound-Repka experiment, again the reference is given about a gravitational redshift, uh, proved that this existence of gravitation spectral shift and expansion of mass, space, and time that was predicted by general relativity. So about special relativity and general relativity, there's experiments that kind of, partially, at least partially confirm about their correctness. But there are a lot of questions still. Uh, so the gravitational redshift is seen as, as study of stars, star systems, galaxies, uh, as well as pulsars and different aspects, shows the gravitational redshift. And the black hole, of course, studies the biggest aspect that's going on. So Shapiro delay experiment, that's called the fourth test of general relativity. Here, the radar, we know the radar is a real thing. In mesoscopic, we see that. It's the most useful, maybe one of the most useful physics experiment, as we that I mentioned the previous, episode 2, 3, when I talked about the Maxwell thing. That essentially confirmed Maxwell aspects, and also the electron and presence of positrons and the electron photon interaction. That Einstein got the Nobel Prize for photoelectric effect, things like that. But the radar signals passing near a massive object take slightly longer to travel to a target, okay, and longer to return than they would if the mass of the object were not present, or gravitational time delay. This is called gravitation time delay. Gravity essentially exists because of the mass. The general relativity says gravity is not a fundamental. It's because the matter curves the space-time that it creates the gravity, which then, you know, affects the mass. So that's how the frequency is coming into picture. And so the radar signals, in a way, confirmed that Shapiro delay. Now, each of the experiments have their own, you know, questions we have to still answer. So the LIGO gravitation wave experiment, uh, that was fairly recent, that shows the observation gravitation from binary black hole merger. So this originates from the merger of two black holes. So black holes, when they merger, there's a high level of interaction that produces gravitational waves. So that, this was predicted by Einstein general relativity, uh, theoretically, and it was proven in a way by this observation of the binary black holes. Again, that was very tricky because originally black holes never supposed to give out because the light is stopped by the light. There is no information coming. But then uh, eventually, Stephen Hawking, Professor Hawking showed that actually, the called Hawking's radiation can give us information. So that's how the black hole specific instruments like LIGO came up, and other experiments that proved an image black hole, so to say. And also, Chandrasekhar also proved about the limit and also black holes. So all those telescopes which are named after these scientists, Einstein telescope, Chandrasekhar, different types of telescopes, and James Webb now, and also I'm sure a short side also may have Planck. So different types of telescopes give us information about that. They provide a cosmic symphony, supposed to, echoing the dynamic dance of massive objects. So if you look at gravitation, they look like a musical, symphony or harmony that's going on in the nature. So you get vibrations, which eventually become the sound aspect that we see. So there are pressure waves that's created essentially by these massive object interactions. So when we look at all through, we start from classical, then relativity, modern quantum to contemporary physics. When you look at that, uh, one of the things that was outstanding was the Arthur Eddington's, Sir Eddington's experiment, telescope experiment during the solar eclipse of 1990. Uh, and that was prediction. Generality says that you will see this bending of light theta, which is related to the gravity because of gravitation. Gravity affects the electromagnetic radiation. It bends that. So it was that it should be 1.75 arc seconds. So observed radius of the sun as a unit of measure, double the distance of star from the center. The deflection decreased by half. Okay. So according to this formula, and three times the sun's radius, the deflection is one third and zero point 0.6. So these different differentials were measured by Eddington and his associate Dyson Sphere and also Davidson. So they determined the deflection of light, but sun's gravitational field during the observations of total solar eclipse of you know May 29, 1990. This is a this is a fundamental thing that shifted from classical to relativistic physics in some sense. So classical physics key concepts are force, mass, acceleration, energy. We know they are scalar; they can be measured uh, pretty easily, and that's what we use in everyday life. The weight of an object, for example, in specific case. The relativity, special and general. The key ideas are time dilation, special relativity, length contraction, then the equivalence of energy and mass at the quantum level, which is E equal to mc squared. Gravity as the curvature of space-time due to massive objects, gravitational waves, and equivalence principle of acceleration with gravity. That study. So the equivalence principle may be the uh, you know holy grail of this general relativity, whereas for quantum physics may be the correspondence principle, as I mentioned previous episodes as well. So the modern physics with quantum mechanics, wave particle duality, the key aspects is the quantization of wave and particles, wave functions and quantum states. So essentially, it's a field. You can think of particles as a condensed field. So that's a quantum field theory came to be. But they are advanced. So the quantum field theory, then electromagnetism, quantum chromodynamics. Of course, you have to advance it to quantum chromodynamics, and we know for for strong interactions, we have the octet structure and things like that, which is color charges. Uh, Quantum chromodynamics in the picture, and quantum entanglement. And the key phenomena there is superposition, like I mentioned about the photon pair interaction, superposition. The photon pair can be quantum entangled. Tunneling aspect, I mentioned about scanning tunneling microscope. Tunneling aspect, quantum teleportation. So which talks about we can actually teleport a quantum level information in terms of spins. So it can be, electrons can be swapped around to particles. Eventually, electrons constitutes the matter somehow. But in the larger mesoscopic level, that's still a question. Question whether it can go through a wormhole, things like that, or the drives, hyperdrives, superluminal speeds. These are all things that come out of it, but they are kind of fictional right now. Like Acubere drive, things like that are supposed to be more realistic, but still they are very far. They're still fictional aspect of the of it. So essentially, what we are saying is that you know, let me put it back. Sorry, I think I had to put it back again. Uh, ensure that I have that. All right. So the contemporary physics string theory is one of the things like it's fully mathematical. Dark matter again there is no particular proof. Even the WIMP, which is called weakly interactive massive particles, now they say it could be. We are talking with Emmanuel that it could be. He's talking about the gravitonic superluminal aspects, and The dark matter, is still a question whether that's to explain, about the astrophysical aspects, measurement of the movement of astro objects, dark energy. So it's associated with the Hubble space expansion, things like that. Okay, these are all questions that there are no real uh, experimental proofs for these. Quantum computing is a real thing. I mean, the computers are coming up, and it talks about, it's not just binary, but you can have a superposition of one and zeros, and that's a developing area. So again, these instruments indirectly proves about the quantum aspects. So the quantum physics generated catastrophe, however, is a very important aspect we have to address. So, like I said before, the ultraviolet catastrophe before quantum physics, classical physics predicted black body radiation. Flow of a heated object would increase without bound as the frequency of radiation increased further. So that was a big problem. So Planck came up with the solution max catastrophe by introducing concept of quantized energy levels. The proposed energy is not continuously divisible but comes in discrete packets, and this has been kind of proven that atomic transitions, they don't occur continuously, but you have to have certain amount of energy before the electron will jump to the next orbit, things like that, orbital physics. But then that promulgated another level of a problem, which is vacuum catastrophe. So, which is quantum theory suggests vacuum energy density, so known as cosmological constant, should be infinite due to quantum fluctuations with pure particles. Uh, we know particles pop in and out of existence, uh, especially in the vacuum. However, theoretical prediction of vacuum energy is many orders of magnitude larger than what we observe, creating significant mismatch. This is called cosmological constant problem. Vacuum energy constant is a possible explanation for dark energy having negative pressure, causing repulsive gravitational effects permeating all of space. So there are some explanations like, uh, you know, of negative pressure, things like that. So negative energies, negative pressure. So if we talk about symmetry in a larger sense, if there is a positive thing, there should be a negative thing. Something like that. So these are all ongoing. Uh, you can look at the references, which are private radiation and vacuum catastrophe. Okay. So the standard physics versus exotic physics. So as we said, I talked about October thing. So there are exotic physics that comes out of quantum mechanics. So there's standard physics. So standard physics, which was originally the normal physics, was classical, but it shifted to quantum relativistic physics, right? With some experiments I showed you. There are a few more experiments. I have not listed all of the experiments. I gave a sample of the experiments that showed how the quantum relativity could be true, general relativity could be true. The standard model, which developed eventually, putting together all the understanding of quantum physics, the framework describes fundamental particles and their interaction, and that's very similar to you created a table of particles very similar to our, elemental driven chemistry, chemical elements, called periodic table. So it's very similar to periodic table. It's kind of like periodic table particles, you can say. Quantum mechanics governs the behavior of particles at atomic and subatomic scales. So we know the energy is quantized, how they work is what quantum mechanics talks about. So electromagnetic weak nuclear force and strong nuclear force. So we know they should be interconnected. The three fundamental forces in the standard model. So the standard model tried to unify them together. But the question of gravity is still, like I say, up in there. So in relativity, Einstein's theory of gravity explaining large-scale phenomena like planetary motion and black holes, is still in play, but there are a lot of questions regarding that. So the exotic physics that I talk about, string theory, can be considered that because it's a mathematical thing which is there is no proof. An ambitious attempt to unify all forces and particles into single framework. The concepts are fairly simple. I think we are using those simple concepts of open strings and closed strings, loop, to describe weak gravity, strong gravity, things like that. So there are some things that the conceptually could be used for some things for developing higher level models. Uh, Symmetry. Hypothesis hidden symmetry between particles with different spins. So the particles among them, it's called group theory as well as using group theory. We can talk about the supersymmetry. It's called SUSY, uh, unitary groups, things like that are developing aspect. Then you have extra dimension that I talked about the previous episodes as well. Extra dimensions. String theories propose additional spatial dimension beyond familiar tree. So we have the Euclidean or thing, but there should be higher dimensions. The extra dimensions could be 10 or more dimensions according to string theory. Dark matter and dark energy, mysterious components in the cosmos. So, uh, the question of mass gap also comes into picture in this. But so these set of references give us understanding, and that some theories are much more realistic, and they may be giving correct answers in many respects. Then we'll say quantum chromodynamics. One of the fundamental people who talked about that. Then the introduction to bosonic string, superstring beyond, like photons or bosons, for example. Then we have supersymmetry and extra dimensions, again for Cambridge. Unique theory of dark energy, dark matter, negative masses. So even it proposes negative masses to explain that matter creation. Uh, so new things are branched like information, exotic smoothness and physics, things like that. So all these are things that are upcoming aspects. So this we look at a little bit on the standard model, like I mentioned, is like a periodic table of particles, right? In a simple sense. Uh, so we talk about particle physics. It's very closely connected to quantum field theory. Feynman diagram is the one that has helped people to calculate uh, all these parameters to come up with this standard model. And it has understanding of spin zero, which is called the Higgs boson. Then spin half, fermions. Spin one, it's a gauge boson. The light, for example, the photons are connected with the gauge bosons. And then there are a lot of descriptions. I'm not going to go into detail. You can look into that, or you can expand that. But essentially talks about the fundamental basis for that. Higgs field, things like that. Then you have the quark, non quark. Uh, they are also the muon. The electrons itself have different different masses, have muons and tau particles, things like that. So they all interact together, and the electroweak theory, in a sense, proves this aspect. The broken symmetry. So the symmetry is a very important part in these processes. And then we have the special unitary matrix SU3, SU1. So this is a group taken from which explains many of things, and U1, you have the gauge fields, which are SU3, SU2, and U1, which are the matrices, you know, the 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 dimension of the matrices essentially. So these can be seen under this uh, mathematical formation standard tree, and this is kind of proven. Many of the things are proven with the Large Hadron Collider and the other particle accelerators. Okay, so sorry for this is such a is kind of little crowded here. Many of them. So essentially, we are talking about Lagrangian symmetry. Lagrange talks about the energy, kinetic energy minus the potential energy. Essentially, is Lagrangian. Talks about the motion equation of motion connected directly with the equation of motion. So the Lagrangian symmetry is very. The transforms are so critical, as I mentioned in the previous episodes, to understand the physics. Especially beyond the classical physics. The electroweak interaction, quantum chromodynamics is its mechanism. They are some of the highlights of the high-level quantum aspects. The electroweak interacts with the symmetry group U1, uh, and then SU2, where the subscript L indicates a coupling only to left-handed form. So this is one aspect, the left-handed versus right, and that's ongoing aspect. Um, Only left-hander for me. But maybe like Christopher, like we were discussing before the manual, that the right-handed may be imaginary, for example. So this is quite possible. But the Lagrangian is a combination of all that. Uh, so combine all that, we can describe a Lagrangian. And one of the recent papers I did prove that what I developed, if I reduce to classical physics, get a Lagrangian that proves equivalence principle, things like that. So that's very exciting area uh, to explore further, especially the mathematics of it. Uh, so B1 in this case is B subscript mu. So it's a general coordinate. Mu are the general coordinates where we use Euclidean, they are orthogonal coordinate XYZ. They are orthogonal coordinates, very simple. But then you have to use that with the Riemann geometry, general coordinates, so that we can describe the curvature of especially moving system. And you have Euler angles, geometry of highly dynamic systems, which changes the coordinates itself. So the coordinates have to be constantly changed, and then mu helps in that aspect. So B mu is one gauge field. So gauge theory, gauge symmetry. I think they mentioned before is another field where the invariance aspect, invariant symmetry, like that aspects come to, and then Lie geometry, and then it talks about how they are similar in terms of pattern analysis. So here, Y2 is a weak hypercharge generator of U1 group. So we talked about generators and annihilators. Uh, and W is the three-component SU2 gauge field. The gauge fields are, invariant fields. So we can, talk about a classical physics, everything we interconnected to gauge theories. Components of tau are the polymatrices. The polymatrices, fundamental matrices, talk about quaternions, quaternionic aspect, the imaginary, the Schrodinger equation does have, like I mentioned, that have imaginary component as well as real components. So that's something we have to do. Inferential generators of the SU2 group, whose eigenvalues give a weak isospin. So this again is a hot area, understanding weak isospins, because electroweak theory has been proven to be much more realistic, and then probably that's That may be the key which proves the standard model and also going further, something that you have to consider deeply. All right. So we have to find a new U1 symmetry of weak hypercharge different from QED. QED is quantum electron dynamics to achieve the unification with the weak force. So that's a big thing that's going on. Can we unify weak force, weak theory with gravity? That's an open question. The quantum chromodynamics, QCD, defines the interactions between quarks and gluons. So we know that all the particles now, including proton and electron, all the way up to proton, hadrons, and fermions, and all that, they are consist of quarks, described in terms of quarks and gluons, Gell-Mann matrix. So a SU3 symmetry generated by by this aspect, by the stress tensor, since leptons do not interact with the gluons, so the interactions have been proven. Uh, the leptons, which consist the fermions and all, they don't interact with gluons. They are not affected by the sector. The direct Lagrangian of the quark is coupled to the gluon field. So uh, the Lagrangian we talk about, we can derive the Lagrangian and how they to each of the fields. For example, gluon field, you can talk about Lagrangian of QCD can be described through Dirac formulations of the uh, uh, of the quarks for the quarks and gluon. So U and D are the Dirac spinors. So we come up with the spinors that connects them associated with up and down type quarks. And other notation are continued from previous. Okay. So the Higgs part, which is the Higgs boson, is the one that gives mass. Like so again, that Lagrangian is connected with you know uh, for different sectors. The mechanism of spontaneous symmetry breaking. So it involves symmetry breaking because the mass formation in the Higgs boson involves the Higgs symmetry breaking aspect. Okay, so there's a parameter hidden within the shape of the potential. It depends on the Higgs potential, hat type, McLean hat type potential gradient, and then that is connected with the symmetry breaking aspect. Uh, Many other people are even questioning of the Higgs mechanism because then the world cannot exist anymore. The recent uh, uh, papers talk about if the exact Higgs mechanism were true, then they'll be annihilated by the black holes, and the real world, the observer universe that we see, cannot really exist. So these questions are really upcoming. It has been proven, of course. The previous episode, we showed that Higgs boson had been proved by LHC experiments, and Higgs got the Nobel Prize for that. So very important unitary gauge, one can set this parameter to be equal to 0 and phi 0 as real. So we want to create real scalar aspects, scalar fields, maybe even we call the scalar gauge fields. Then managing vacuum expectation value. So this is where the vacuum expectation value come into being, like I mentioned before, the vacuum catastrophe eventually. But the vacuum expectation value of the Higgs field has non-dimensional. So it has dimensions, and that is something that proves about the Higgs boson. It's also much smaller than the Planck scale, and it's about so that Planck scale sets the right if particles there is a finite size, the particles have dimensions, but below the Planck scale they may exist only as quasi particles or partons or unparticled things like that. We develop a hot mechanics when we think that it's unparticle. Um, but in any case, uh, it's smaller than the Planck scale, twice the Higgs mass. Okay, So so this is the mass, you know, that's denoted by this new aspect, setting scale for mass of all the particles in the. So we want to see what you call we use uh, a reference mass or calibrated mass, or we use standards, right, for based on certain aspects, like for length measurements or time. So there is a standard way we talk about uh, these for, for atomic clock. We have the quartz microcrystal. Now there are more things coming. So quartz crystal was one of the oscillations associated with this fundamental. For length, you have the standard of length that is measured in France and other places. We use for potential, for example, we use hydrogen electrode. And so there are ways and a mass, we use certain standard the mass that can be measured in a specific environment, if like that. These are all continuously changing, but we know the mass doesn't change. Mass is, you know, more general than a weight. Weight depends on the gravity. So the mass is the content of the matter contained within it. So we want to understand from a very much simpler than even normal physics can explain about this aspect, because you want circular logic to come into picture. So you want to avoid that, and then see how we can explain these aspects. So that's the newer aspect. And what is the most fundamental aspect? Could be noise. That's what I'm coming. So all this creates noise because very high levels, if they have such interactions and also symmetry, it may all create noise which we cannot observe. So that may be explained about dark energy, dark matter. But that's something to see further on. So thank you very much for your attention and in this, and we'll continue our discussions about this method. We will continue to episode 6 and all. So the next aspect of the upcoming episodes will be to understand. For example, there's a question you can think about: the energy getting divided into two parts. Uh, Quantum physics, which talks about space and time. Generality talks about electromagnetic and gravity. Is that the way the energy is divided? And if so, maybe that will explain the vacuum construction. We are comparing apples and oranges in some ways. Quantum physics talks about space and time may be hidden, like my research has shown, and the space. So they behave differently in the quantum level. Generally, the main thing is the light aspect. We're talking about astrophysical aspect mostly. So this is micro level, it's macro level, or even astrophysical level, which is the mesoscopic mixed aspect of the micro and macro. So we have the electromagnetic and gravity come into picture, and all of them are interplay. Whereas they get separated, right? The quantum level, it's like you have vacuum. You can separate, you know, any atom. They get ionized, and you get ionic aspects. So they get pulled apart into their fundamental particles more and more, and they eventually become positrons and electrons, so to say. So that's what quantum physics talks about. So the regime of the quantum physics different from that of the general, where generality considers the interaction of the electromagnetism with gravity. So the episode 6 to 10 will continue analyzing the quantum field theory. So we have to continue that. It's an ongoing method of feedback circuit, so to say. So we'll go back and forth on this. That's one of the aspects that is very excruciating, in some sense, very involved, because we have to keep using them back and forth, back and forth. So we'll come back again to quantum field theory, the software string theories, see how they all come together, and like that. eventually to quantum gravity. And the quantum gravity is developed all the way, lattice quantum gravity, things like that. And there are different types. Uh, they become more mathematically abstruse to some degree. Supersymmetry, again, that's concept. And then the breaking of symmetry and things like that is, again, and a vast area of current research, exciting research that's ongoing. Then come up theory of everything, which includes all the four forces, the the weak force, the strong force, the electromagnetism, and the gravity, all coming together. What the fundamental, the quanta and the field that Sean Carroll, for example, is talking about. And then you need furthermore, uh, there are a lot of gaps to be filled in, and we know uh, the mass gap theory, uh, you know, theory aspects that talks about power coupling and you know uh, and other aspects. So we will continue in this process uh, to dissect through all these aspects, and hopefully we'll get a better picture, but without any speculation. We just, in the history of physics, we are presenting the way what we know it is in terms of the theoretical development, in terms of the experimental things that kind of partially at least partially confirm all the aspects. So that's very important, not only experiments but also observations. And then reductionism, which means that if we reduce certain conditions, dilute certain condition, or relax certain conditions of quantum mechanics, that should conform the classical aspects. The same with relativity. So they all should, coagulate or reduce to classical physics when you apply certain conditions for them, right? Uh, Under relaxed conditions, they should conform to classical theory. So these are the aspects that's going to be analyzed, and then further modeling and simplifications uh, will occur as we go along, and use Occam's razor to explain the thing. So these are the main aspects. So thank you very much for your attention, and and then we'll end the presentation today, and we hope to continue. You know, every month we will have this episode uh, that we continue, um, and then we'll go on to the next episode 6, probably in September sometime, and episode 7 in October, and episode 8 in November. And then we hope that the episode after that, we'll take stock of the situations and what's happening, uh, and then see whether, how the episode 9 and 10 will shape up based on our detailed Q&A, and also discussions, debates, things like that. That will decide the aspect, because we are, like I said, we are go back and forth with all these high level theories, and there's also M theory that I will touch upon the later episodes, which are talks about the brains and the all other aspects, the how these structures develop, you know, like a Fourier, using Fourier and the blank sheets and things like that, how they could develop. So these are exciting areas, but the experiments are becoming more complex and very hard to prove many of the theories. And that keeps these in question. I'll continue to dissect that and see where mathematics itself, can be converted into simpler physics or experimental physics. That will, if proven, we can go back and say, okay, these are correct. If these are correct, those are correct. We can put conditions like that, and so the IT aspect come into picture, the programming and the coding that we are working together as we go on, and with Christopher especially, and the manual experimentation. We hope to have a better picture of physics developing, as we go along each episode. So thank you very much for your attention. And we will right now uh, we'll discontinue this aspect now, and then we'll pick up on that later on. Thank you.